Alright guys, welcome back to Underground Science, and in this video we'll be talking about the photoelectric effect. Alright, so before I lay down the basic definition of what photoelectric effect is, of what the photoelectric effect is, I'm just gonna say that it's probably not gonna make a lot of sense when I explain it right now in like a short definition. But I promise you that once we're done with the video working problems together, we'll come back to the definition that we were just about to say, and I promise you'll make much more sense. All right. So again, we'll be talking about the the photoelectric effect. All right. So so let's just start off with the basic definition. All right, that I can think of right now. So the photoelectric effect is the amount of energy a photon needs, the amount of energy a photon needs, and a photon is just a light particle, all right? So the amount of energy a photon needs, or a light particle needs, right, which is pretty much a photon, to overcome, all right, so this is going to be the weird part, to overcome the work function, all right, the work function. Okay, I know you're just like, okay, what's work function? All right, stop saying random things and get to the point, but I'm about to, all right? So the energy a photon needs to overcome the work function of a metal, and that metal, if the energy of or if the photon has enough energy to overcome the work function of the metal, then that electron that the photon collides with in the core of that metal will be freed to the surface of that metal. All right, so if all this happens, if the energy of the photon is greater than the work function of the metal, the electron that the photon collides with will be freed to the surface of the metal. All right, so we just said that, but that probably made no sense. All right, so let's just go ahead and get started and talk about the photoelectric effect, and we'll come back to this definition and it'll make much more sense. All right, so first off, what's work function? All right, so the work function of a metal, all right, so one thing we need to know that the work function of a metal will vary metal to metal. Okay, so each metal will have its own work function. Okay, so I'm just going to say vary, or let me say will vary from metal to metal. Okay, so it's going to be different. The work function will be different for each metal, right? So from metal to metal. Okay, so now let's talk about what work function is. So the work function of a metal, let me go and write this down real quick. The work function of a metal is the amount of energy, and in joules, okay? So energy is going to be in joules. So the work function is the amount of energy it takes to free the electron in the core of that metal, to free the electron in the core of the metal to the surface of that metal. Okay, so of that same metal to the surface of that last word metal. Okay, so the work function is the amount of energy it takes to free that electron. All right, so you know what, let's just think of this as arm wrestling. Yeah, that's a good example, arm wrestling. Okay, so let's say you start right in neutral positions with your arms up, and you're like, all right, bro, 1, 2, ready, go, and you start. Okay, so think of the work function as the amount of energy that you need to put, right, the amount of energy that you need to expend for your muscles to overcome his energy that he's expending on you, okay, on your arm. So he's trying to put your arm down, you're trying to put his arm down, and you're stagnant and you guys are shaking, and you put that extra energy, right, just to put his arm down. And that extra energy that you put in order to put his arm down is the work function, all right? If you think of it as an analogy to this photoelectric effect, all right, that's the work function, the amount of the extra energy that you put and that makes his arm go down, all right, and you win because of the extra energy. Just like that, this is the amount of energy, right, that extra energy it takes to free that electron from the metal, okay, from the core of the metal. So again, just related to arm wrestling or something that, in real life. So it's going to help you understand the concept more. All right, so that's all work function is. It's the amount of energy in joules it takes to free that electron in the core of that metal to the surface of that metal. All right, and now you're probably wondering, all right, well, how is that electron going to get freed from the core of the metal? Well, that's what the definition was, right? Let's go up and see. Nope, that didn't work. Let's go up and see that the definition we just said was the energy a photon needs to overcome the work function of a metal, all right, and free that electron to the surface of the metal. Okay, and that's pretty much the idea of photoelectric effect. And if that, one thing I should mention, that if the energy of the photon is strong enough, if it's greater than the energy of the work function, then what does that mean, right? That means you put more energy and you put his arm down first, okay, if we're relating to arm wrestling. So think of your energy that you're trying to put to win as the energy of the photon, and the work function, think of it as his maximum energy that he has in order to stabilize your pushing of his arm, okay? So he can't take it anymore, so he just gives up. That giving up is the work function, okay? You overcame his work function. Just like that, if a photon, all right, if the energy of this photon overcomes the work function of that metal, then that electron that this photon collides with in the metal will be freed to the surface. And if, and only if, the energy of the photon overcomes the work function and the electron is freed, then that electron is going to be called the photoelectron. All right, and that's why you can see the name of this whole idea is the photoelectric effect. All right, due to the photon, or the energy of the photon, we freed an electron if it's greater than the work function of that metal. All right, so I hope that made little sense, at least to get started off with. All right, and so now that we know that, one last thing before we move into a few examples is that for this video we'll need to know a few equations. All right, so I don't even have space. All right, right here. Right, so I'll just write it right here. So the first equation that we should know is that energy. So you know how we're talking about the energy of the photon if it's greater than the work function? Well, that equation is the energy of the photon is going to be equal to the Planck's constant times the frequency of that photon. All right. And the next equation we'll have to know is that the speed of light, all right, the speed of light is equal to the frequency times the wavelength. Okay, so now that we know those two equations, that'll help us in our example problems. All right, so let's go ahead and scroll down and let's work together to solve these example problems that we have. All right, there's only one here, but there's another one on another page. Okay, so let's read this and understand what it's trying to say. All right, let's say we have an alkali metal. All right, so let's say we have an alkali metal, and the alkali metal is rubidium. Okay, and remember, alkali metals are on the group 1 of the periodic table. All right, so we have an alkali metal, rubidium, and moreover, the work function of rubidium. All right, so now we know what work function is, right? The amount of energy it takes to free that electron and for that electron to become a photoelectron. Okay, so the work function of rubidium, which is our alkali metal, is around 2.11 electron volts. Okay. Also, we have a photon with a wavelength. Okay, we have to focus on that, with a wavelength of about 600 nanometers. And that photon will collide with the rubidium metal. All right, because remember, we need a photon that's colliding with the metal so that when it collides with the electron, the core electron, that electron can be freed if the photon, or if the energy of the photon is greater than the work function. All right, so actually, you know what, we forgot another very important equation. All right, so that equation is going to involve kinetic energy, the work function and of the metal, and the energy of the photon. Okay, so let's go and write it down here. Oh, actually, you know what, let's just read the question first. So we read that. Now the question is, what is the kinetic energy of the electron in the core of the rubidium metal? All right, so what's the kinetic energy of that electron? So one thing to know, kinetic energy is what? 1/2 mass times velocity squared is our kinetic energy. All right, if the energy of the photon is greater than the work function, we said what would happen? That photon will collide with the electron, right? If that photon's energy is greater than the work function of the metal, when that photon collides with the electron and the metal, that electron is going to be freed and become a photoelectron. When that electron is freed, all right, so let's say we have our rubidium metal right here, right? I'm going to try to draw like a cube for 3D. So let's say we have rubidium metal right here, right? And we have like a bunch of protons in its core, and we know opposite charges attract, right? So our electrons are trying to get attracted to this, right? And let's say a photon tries to come and invade the party, all right? So what color should we draw that with? Let's draw dark orange. All right, so photons coming, and this is our metal, right? This is our rubidium metal, so let me go and write that down. This is our rubidium. All right, and let's say a photon comes and he's like, yo, I want to join the party. I want to take an electron with me, all right? So I'm going to collide with you, metal, okay? I'm going to collide with you, rubidium, and if the work function is less than the energy of the photon, then we know that the electron will be freed and become a photoelectron. All right, so let's say it is. Let's say the energy of the photon is greater. So let's go and write that down. Let's say in this scenario, the energy of the photon is greater than the work function of the metal. And that would mean that the electron is like, dang, I gotta go, guys. All right, so he goes and ends up on the surface of the rubidium metal. As he went, he had velocity, all right? The electron had velocity as he got knocked off. And that velocity means that that electron will have some kinetic energy, okay? And so we know that because an electron and kinetic energy can't be negative, right? Because the velocity is squared. So even though the velocity is negative, if you square it, it's going to become positive, and we know you can't have a mass that's negative. Okay, and an electron's mass is about 9.11, so let me go and write that down. Mass of, nope, no, that's not good. Come on, you gotta erase that F. All right, so mass of electron is about 9.11 times 10 to the negative 31st, all right, kilograms. And let's just work with kilograms in this example, right? Let's use kilograms for mass so we don't have to convert to grams, all right? So if we feed 9.11 times 10 to the negative 31st kilograms into the mass, and we know that because this electron got freed, it's going to have some velocity, so that velocity squared is going to have a positive kinetic energy. And it's, I mean, I'm saying it like there's going to be a negative, but kinetic energy is not a negative value. It's always going to be a positive value. All right, and since we're talking about energy, we're going to be talking about, in the units of joules. All right, so knowing that concept, let's try to solve the question, okay? So what is the kinetic energy of the electron in the core of the rubidium metal? All right, so first step, what do we do? Okay, so let's write down our equation that we were talking about. Okay, kinetic energy is equal to the energy of the photon. All right, so the energy of the photon minus the work function of that metal. Okay, actually, wait, so since we're labeling things, the kinetic energy of the electron is what we're trying to solve for. See, we said that right here in the question. So kinetic energy of the electron is equal to the energy of the photon in joules. So let's go ahead and make this as clear as possible as we can, so it's going to be easier for us when we solve the problem. Energy of the photon in joules minus the work function of the metal, okay, of the metal. Okay, and so that makes sense because if the energy of the photon is greater than the work function of the metal, that means that we're going to free that electron to the surface of that metal. And if we do that, we know that that electron will have some velocity, which means that electron will now a photoelectron, right? Because it got freed. That photoelectron will also have some kinetic energy. All right, so let's go ahead and try to solve this. All right, so now that we know this equation and we're trying to solve for the kinetic energy, right? Our first step would be, all right, let's figure out what the work function of the metal is. So let's go and see if it tells us that in the problem, right? So we're reading, oh, right here. The work function of rubidium is around 2.11 electron volts, okay? And we just said above that work function, actually we didn't even say it here, the work function is in joules, okay? Because this is also an energy, the amount of energy it takes for that electron in that metal to get freed, right? So, but over here we just saw it says that the work function is 2.11 electron volts. Right, so we're like, all right, what do? We have to convert electron volts into joules. So guys, let's go ahead and do that, okay? So we have a conversion factor here to help us. 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. All right, and if we know that, we can figure out how many joules is equal to 2.11 electron volts. So we just probably already know, like, oh yeah, just multiply, but let's just show the proportion. All right, so we know that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So 2.11 electron volts will be equal to how many joules, right? X, we don't know, right? I mean, we know we just multiply, but we're doing it for the sake of proportions. So we just cross multiply here, right? And don't worry about the units much because we're just setting up this proportion for our sake. All right, so we know that we're trying to find joules here. So we're gonna cross multiply and we're gonna get X equals 1.6 times 10 to the negative 19th joules times 2.11 electron volts. And what do we get? We get X is equal to about 3.376 times 10 to the negative 19th, and we know we're trying to find joules, so our units are going to be joules. And again, we just found the work function of rubidium in joules, okay? We were given the work function of rubidium, our alkali metal, in electron volts right here, but we had to convert that into joules because we know that the units for work function is in joules. All right, so let's go ahead and label this. This is our work function for what, right? We said for rubidium, our alkali metal that we're working with here. All right, sweet. So we got that now. So we have 1/3 of the equation down, right? We have our work function down, which we just calculated. Now we have to figure out, so again, we're trying to find the kinetic energy of the electron, if it's freed or not. We don't know if it's freed. We're trying to see if it is by, all we have to see now is if the energy of the photon is going to be greater than this value right here, 3.376 times 10 to the negative 19 joules. If the energy of the photon is greater than our work function that we calculated here, then we know we're going to have a photoelectron, right? Because that if the energy of the photon is greater than the work function, the electron in the core of the metal will be freed to the surface of that metal. Okay, and so let's go ahead and calculate the energy of the photon then. And remember, we went over the two important equations. So right here is our amazing equation that we're going to use, and we're actually also going to need this equation on top of that, okay? So let's go and work with these two equations and figure out the energy of the photon together, all right? So let's go and write that down. So the energy of the photon, I'm just going to say energy of photon right here, all right, is going to be equal to the Planck's constant, which is 6.626 times 10 to the negative 34th meters squared. Meters squared times kilograms over seconds. All right, so that's a lot of units. So for now, let's just leave. So you know what? Let's just go and write that down, and then we won't have to worry about the units. All right, let's just work with the number. So we said Planck constant was 6.626 times 10 to the negative 34th meters squared times kilograms all over seconds. All right, that's the units for Planck's constant. But to get the actual value, we'll just focus on the number itself. But for reference, we know the units. All right, meters squared times kilograms over seconds. All right, let's go back to the equation. So H times F. All right, frequency. Okay, so we know, so H is a constant, Planck's constant, so we know that value. How do we solve for F? Well, let's go back, okay? Let's see what our question gives us. So we said that also we have a photon with a wavelength of 600 nanometers. All right, so that's our key thing right there, 600 nanometers. All right, well, nanometers, we just said, the problem just said is the wavelength of the photon. So we need frequency of the photon. So how is that supposed to work? Well, now this equation comes in handy, right here. The speed of light is equal to, so c is a constant, speed of light, is equal to the frequency of that light times the wavelength. All right, so right there we see the frequency, so all we have to do is just solve for frequency in that equation. All right, so let's go and do that. So c equals the speed of light, or that is the speed of light, equals frequency times the wavelength. So then frequency will equal speed of light over wavelength. Perfect. Now we finally have frequency. So we just have to feed that into this value right here. All right, so we're going to say the energy of the photon, actually we'll say right here, the energy of the photon, energy, okay, I can't write, wait, energy of the photon is equal to, bring it down here so it can be more clear, is equal to the Planck's constant times the speed of light over the wavelength. All right, now we have all the values, right? Planck's constant, we just said was 6.626 times 10 to the negative 34th meters squared times kilograms over seconds. That's a constant, so we know that. Speed of light, constant, right? We know that too. It's about 3 times 10 to the 8th meters per second. And we know the wavelength, right? Because we got told that in the problem, right? Where is it? Right here. The wavelength, we have a photon with a wavelength of 600 nanometers. But one thing we have to be very careful of is that the wavelength in this equation is not in nanometers, it's in meters. So we can't make the mistake of putting nanometers in here or we're screwed, okay? So this is in meters. And we know that in 1 meter, we have 1 billion nanometers. All right, so that's an important conversion factor that we should know. So let's go and write that down. So 1 billion, okay, 1 billion, no, that's not good. Erase that for a sec. So we write that word, all right, 1 billion nanometers, or I'll just abbreviate as NM, is equal to 1 meter. All right, so that's how small nanometers are. All right, so remember we have to feed in the meters. All right, so how many meters are in 600 nanometers? Well, remember 1 billion nanometers means we have 9 zeros. All right, so that means 600 nanometers, right? That's what our wavelength is for our photon in this problem, is going to be equal to 600 times 10 to the negative 9th, all right, meters. And we said 10 to the negative 9th because there's 9 zeros in 1 billion. All right, so now that we have that, we can literally solve for the energy of the photon. Okay, so let's go ahead and do that. All right, and we don't have any room left. All right, so let's just go to another page real quick. And here we are. All right, so this is where we left off in the previous page, right? So we talked about the work function. We calculated that to be 3.376 times 10 to the negative 19 joules. Then we said that 600 nanometers is equal to 600 times 10 to the negative 9th meters, because 1 meter is equal to 1 billion nanometers. All right. And then we had our equations, right? We said energy of the photon is equal to, so the energy of the photon is equal to the Planck's constant, which is 6.626 times 10 to the negative 34th meters squared times kilograms over seconds. You know what, let's just go and write that down all the way at the top, all right? So Planck's constant, denoted as H, is equal to 6.626 times 10 to the negative 34th meters squared times kilograms all over seconds. All right, again, those units are huge. Just to get the concept down, we'll be more focusing on the actual number, all right? 6.626 times 10 to the negative 34th. And at least now that we wrote it down, we know what the units are, right? Meters squared times kilograms over seconds. All right, so we have energy of the photon is equal to Planck's constant times frequency of that photon. All right, and then we said we have another equation, which is the speed of light, or else denoted as c, equals the wavelength times the frequency. Oh, the wavelength times the frequency. All right, got to say that better. All right, so that's the speed of light equation. And then we said that the kinetic energy right here is equal to the energy of the photon minus the work function of the metal. We calculated the work function of the metal to be 3.376 times 10 to the negative 19 joules. Then we said, well, now we need to calculate the energy of the photon. So what we did is we went all the way back to this equation where it's like, all right, we have the wavelength of the photon, right? We said that right here. We have the wavelength of the photon to be 600 nanometers. So we went to this equation right here, and we looked at energy is equal to Planck's constant times frequency. And we're just like, okay, how are we supposed to use nanometers and wavelength in this equation right here? And then we're just like, oh, sweet, let's just use this equation right here and solve for frequency and then feed that into the frequency value in this equation. So that's what we did, right? We said that frequency is equal to the speed of light divided by the wavelength, right? Based on this equation right here. And then we took that frequency value, or the speed of light divided by the wavelength, and we fed it into here. And what did that result in? Well, that resulted in this. Energy of the photon, which I'll just write as E, is equal to the Planck's constant times, and let's denote the same color, speed of light over the wavelength. All right. Oh, wait, I just noticed I already wrote it down right here. Okay. But anyways, that's what happened. Okay, so we fed it in, and now, remember, this is the energy of the photon. Now we're in good condition, right? We can find the energy of the photon because we said in the previous slide that we have the Planck's constant, which is a constant, so we already know that value. We know the speed of light because, again, it's a constant, and the problem gave us the wavelength, right? Which is 600 nanometers. All right, so let's go ahead and calculate the energy of the photon, and well, actually, what we're gonna do. This video is getting way too long, and I hope you guys aren't asleep, but in the next video, we'll just leave off right from here. All right, so we'll leave off and we'll calculate the energy of the photon. All right, so see you guys in the next video.